Car on a banked curve. As always, if you enjoy this content, like and subscribe. So, this is an advanced problem, and this is something that you might find in an honors course. So if you're only taking Regents physics, you don't have to worry about this problem. Okay, what we have here is a car that's going around a banked curve. If you've ever watched NASCAR, in the races, they bank the corner up, which helps the cars to go around the corner. It gives them an additional force that's directed towards the center of a circle. And we're going to see what that force is in just a second. So when we see this car going around the corner like this, we're going to draw our diagram in 2 dimensions, looking at it from only this perspective. So when we see this, what we're looking at is the back end of the car as it drives around the corner. So the question is to find the minimum speed necessary to round this corner without either slipping up the plane or down the plane. Now remember, it doesn't actually move up relative to this point. It moves in a straight line, but that direction from the perspective of the car seems as though it's going up the plane. It's only going forward. So remember that we always break up forces in the direction of the plane of acceleration. Now, this is our curve, so if we followed this curve around, the center of the circle is over here. So our plane of acceleration is towards the center of the circle. That's going to be where our centripetal force is pointing. So we only have 2 forces in this case. We're ignoring friction, so we only have the force normal and the force of gravity. Well, none of the force of gravity is in the plane of acceleration, so we don't have to worry about breaking that up, and that's not going to be in our net force equation in the x-plane. However, sum of force normal is up, and sum of our force normal is to the right. So this force right here, the component of the force normal that's acting to the right, we're going to call that Fnx, and we're going to call this upward component Fny. So we can see that this force is going to be our centripetal force, and this force is going to be equal to the force of gravity in the opposite direction, and these 2 are going to cancel, which is why it doesn't accelerate up into the air or crash through the ground. Now, there's another couple of tricky things here, which is that this angle theta, as we've seen before, is equal to this angle theta, and from math, geometry, we know that these 2 must also be the same. So let's go ahead and break this up and solve it. We're doing this problem as a derivation, so we're not going to be putting numbers in. So here's our free body diagram, and we're breaking this up into the plane of acceleration. So we have our Fn y and our Fnx. And we know that this is our theta, so this is our theta here. So when we look at this side, this Fny, what is that in terms of theta? Well, we have a right triangle, and we know that this side is Fn. So if we're looking for Fny, we can do cosine theta. So we can say cos theta is equal to adjacent over hypotenuse. In other words, cross-multiplying, Fny is equal to Fn cos theta. And likewise, if we're looking for the x component, our Fnx, that's going to be equal to this side of the triangle, which is our opposite. So we can say sine theta equals opposite Fnx over the hypotenuse, which is Fn. Or we can say Fnx is equal to Fn sine theta. Okay, so Now let's write our F-net equation. So we'll start with an F-net y, and we have to define our directions. I'm going to call up to be positive and to the right to be positive. So we have our F-net y equals ma, and what's acting in the y direction? Well, we have Fny is up, and Fny is going to be our Fn cos theta minus our force of gravity down. Now, in the y direction, there's no acceleration. It's not accelerating this way or this way, so that drops out to be 0. And we're solving for Fn, so we can bring this mg to the other side because that's 0. Whoops, 0. So bringing that over, that becomes Fg equals Fn cos theta. And if we bring this cosine theta over here and replace this with mg, we have mg over cos theta equals Fn. And I'm just going to flip this to the other side and write it as Fn is equal to mg over cos theta. So now we can do our F-net x. So F-net x is going to be equal to ma. But this net force is acting in the plane of acceleration, which is towards the center of the circle. So that's an MAC. So that's going to be equal to the only force that's acting in the x-plane. The only force that's acting in the x-plane is Fnx. And we know that Fnx is Fn sine theta. We know that AC is v squared over r, and we know that Fn is mg over cos theta. So we can say mg over cos theta times sine theta. We have an m on both sides, so we can divide through by m. And we know from math that sine over cosine theta is tan theta. So that becomes g tan theta. And on this side we have v squared over r. Multiplying through by r, that gives us v squared is equal to gr times tan theta. And then taking the square root of both sides, we end up with the square root of gr tan theta. This is called the Gravitron Problem, and this is a ride in amusement parks where they have a large cylinder that spins around in a circle. And the person stands against the wall and the floor drops out and the person sticks to the wall. So the question is, how fast do you have to spin this gravitron so that the person doesn't slide down the wall? We're going to say that the radius of this is r, and we're going to do this as a derivation, so no numbers. So what forces do we have acting on the person? Well, we have Fg. Now, what counteracts Fg? What keeps the person from sliding down? Well, that happens to be friction between the person and the wall. Now, why is there friction? Well, because there's a normal force. The wall pushes against the person to the center of the circle. The wall pushing against the person, that's Fn, and that is going to be our force that's acting in the plane of acceleration, so that is our net force, that's our centripetal force. So let's start out by writing a net force equation in the y direction. We're going to do like we did before. We're going to call up and to the right as positive. So we have Fnet equals ma equals Ff up minus Fg down, and there's no acceleration in the y plane, so a becomes 0. I'm going to add this Fg to the other side, so that becomes Fg equals Ff. And we can say Fg is mg, and force of friction is mu Fn. Now the person is not sliding, so that means that this is mu s, or static friction. So what is Fn? Let's divide through by mu s. So we have mg over mu s is equal to Fn. And I can just flip this equation around and say that Fn is equal to mg over mu s. But there's no velocity in this equation. So we need to solve for v. And the way that we're going to do that is with an F net x equation. So we have F net x equals ma equals, and what's the only force that's acting in the plane of acceleration? Well, that's our Fn. So we can say F net x equals ma equals Fn. A, we know this is a net force to make something go in a circle, so that's AC, which we can replace with v squared over r. And that's going to be equal to mg over mu s. So masses cancel out. We have one on both sides of the equation. We multiply through by r, so that gives us v squared equals gr over mu s. And we take the square root of both sides of the equation, and that gives us the square root of gr over mu s. Notice that mass is not in the equation. In other words, this is a mass-independent ride. Mass does not matter. All right, we have a ball swung in a vertical circle. So this would be as if somebody is standing on the ground and they have a rope and they're spinning this ball around like this. Okay, so gravity is acting down. This is in a vertical plane. So this ball is going to spin at a constant speed, but we want it to go as slow as possible and still make it around the top. In other words, it's just going to make it over the top. Now, if that's the case, then we don't need to pull down on it. We only need gravity to act as a centripetal force to make it go in the circle. So our free body diagram at the top would be only Fg. Fg would be the only force making it go in the circle. So at the top, we have our net force equation. I'm going to call down to be positive. F net equals ma, and this is our plane of acceleration. This is the way that it's accelerating. So that's going to be AC equals, and then that's going to be the force of gravity. So if we replace AC with v squared over r, then we have this Fg is mg. We have m's on both sides, and we multiply through by r, so that gives us gr, and then we take the square root of both sides, which gives us v is equal to gr. That's the minimum speed needed for the ball to round the circle. But this speed remains the same, and when it gets to the bottom of the circle, now we need some force of tension to lift it up because the force of gravity is working against us. In this case, the force of gravity is acting down, is helping us to make it go around the circle. Here, force of gravity is acting away from the center of the circle, so we need additional force up to help us provide enough force to make it go in a circle. So to do that, at the bottom of the circle, we're going to have the force of gravity down, but then we need an additional force of tension up to help make it go in the circle. So our net force is going to be Ft minus Fg in this case. Now, to keep everything positive, I'm going to call up to be positive in this equation. So we have our net force equation, F net equals mac. Our plane of acceleration is in the vertical direction, so that's going to be centripetal. And then we're going to have Ft minus Fg. So AC becomes v squared over r, and Fg becomes mg. So to solve for v, we know that v is the constant speed that we solved for in the problem before, gr. So we can sub in m, and then that's going to be the square root of gr squared over r is equal to ft minus mg. Well, a square root squared is just going to be itself, so that's going to be mgr over r. And we have an r on the top and the bottom, so those will cancel, equals ft minus mg. So we have mg on this side. We're going to add another mg to the other side, so that's going to make that become 2mg equals ft, or rearranging it, the force of tension is going to be 2 times the weight.